Hello, pre-calculus class, and welcome to our lesson on rational functions, discontinuities, and limits. This is really kind of the ramp up towards calculus, one of the very last couple of lessons in our textbook, and just some really interesting things, I think. So I'll try to go through this quickly, but this is going to be a little bit of a longer video. There's just a lot of stuff to go through that's all kind of interconnected, so I'm going to try to make this into one video. Hopefully I don't ramble too much, but let's get started. A rational function is something that's a ratio of two polynomial functions, right? Think of a rational number, something that can be expressed as a fraction. This is basically a fraction involving two different functions, two different polynomial functions. And so it's right, they define it as p of x divided by q of x, where p and q are both polynomials. So we're going to take a look at just one example that kind of walks us through a little bit of this. A cubic function divided by a linear function here. And so these two functions, we have f of x and g of x, are completely identical in every way. X cubed, 7x squared, 13x, but this last number here, the 6 and the 7, make these graphs look very different. So if we were to take a look at this and try to figure out, like, hey, we're going to look at what is f of negative 2 and what's g of negative 2, and do that algebraically to start. If I looked at f of negative 2, I'd need to just plug in negative 2 for x, and I would get negative 2 cubed is negative 8, negative 2 squared is 4, times 7 is 28, negative 2 times 13 is negative 26, and then plus 6. If I did that all together, if negative 8 plus 28 is 20, minus 26 is negative 6, plus 6 makes 0. And on the bottom, of course, we have negative 2 plus 2 makes 0. So I'm dividing by 0 here and doing it in both cases. The bottom one, the g of x, again, completely identical, but instead of adding 6 at the end, we had 7. So we end up with something that's 1 divided by 0. Both of these, if you remember back to Algebra 2, are undefined, right? Division by 0 is not possible, right? Ask Siri to divide something by 0, 0 divided by 0, or 1 divided by 0, and she talks about how Cookie Monster doesn't have any friends and all of that jazz. But I can't do it, right? 0 dividing by 0 is impossible and mathematically undefined. So if we go and look at the graphs of these, let's see how that kind of shows up. So if I'm looking here, I have these two graphs side by side. The g of x one, right, I'll turn that one on first here. The g of x one, when x is negative 2, that division by 0 shows up as an asymptote. We have this dotted line where it's never crossing it, right? It's dividing by, as it gets closer and closer to negative 2, this denominator is getting closer to 0, and it starts to like blow up. You're dividing by a tenth and then by 100th, which is the same as multiplying by 10 and then multiplying by 100. And so it gets this asymptotic behavior, right? The other one, though, the f of x function, if I graph that, it just looks like a pure parabola, right? Like the two things are very, very different. If I zoom way out, right, at the edges, they look a lot alike. F of x and g of x, they're only off by 1 the whole time. Like they get closer and closer and closer together. But in here, close to that negative 2, where I'm dividing by 0, g of x kind of does this exploding thing and comes back up the negative side. But f of x looks like it's just nice and clean. Right? I can tell, though, and Desmos does this nicely for me, that if I get close to exactly negative 2, there is a hole there. It is not defined because you cannot divide by 0. That is an impossible task. So we see it both ways, but they're showing up very differently. And so I want to take a look at a little bit of why that is here. But before we take a look at that why, I want to take a little closer look at the what. What exactly is the difference between these two things, right? We saw back here that, right, f of x is at doing 0 divided by 0 at negative 2, and g of x is doing 1 divided by 0 at negative 2. And so, right, this 0 divided by 0 is an interesting case, right? 0 divided by anything is usually 0, right? 0 divided by 1, 0 divided by 2, 0 divided by any non-zero number comes out to be 0. right? But anything divided by 0 is usually blowing up off to infinity, right? Like if I do 1 divided by, let's say, something really close to 0, like 1,000th or 100,000th, dividing by that fraction, that small decimal, is the same as multiplying by its reciprocal. So I get these like really gigantic numbers. So with these two things kind of competing against each other, the numerator wants to make the result 0. The denominator wants to make the result infinity. And in that function f, it kind of looks like something is winning out here, right? That at -2, we're doing that 0 divided by 0. And if I look here, right, I can tell there's a hole, but as I get closer to it, it kind of looks like, hey, that hole maybe should be filled by -3, right? Like that 0 divided by 0, if I were to just plug that thing in there, just make a little like -2 comma -3 point, that would fill this gap perfectly, right? It's a nice smooth thing. And if I zoom in on that, you can see that, yes, that's exactly where this thing ought to be. So 0 divided by 0 in this case turns out to be -3. If I could actually divide by it, but I can't, right? If I trace it along here, it does still show me that undefined piece. So let's put a little label in here and say it's not really -2 comma -3, it's -2 comma undefined. It does not work, and we'll even let Desmos do a little trick, make it be a little hole there. So if I zoom out, now I can tell, right, this thing is definitely getting closer to -3. That's what should fill this hole. But yeah, we don't quite know why. One other thing that the book will ask you to do is to make a table of values showing what function f and function g seem to be approaching as you get closer to that place where it's undefined, place where it's dividing by 0 in both cases. So one thing they ask you to do is make a table of that. And so an easy way to do that is to say I have my x1 and I want to make a table with the f of x1 values. Right, again, x1 shows up right there right away. If I want to make a table with the f of x values, you have to type f of x, then just hit the 1 key after it. It'll immediately put it in the subscript there for you. It looks like it doesn't like it. It's got that little exclamation point, but as soon as you put something in, say, I'm going to try to get closer to this thing kind of from both sides. So on this side, I'm going to do like -2.1. -2 is undefined, but -2.1, right? It's at -3.109. It's really getting close to -3. And they say, like, show a table of values where the x is getting closer and closer to that. So they want you to really do this multiplicatively, like try to get right kind of 10 times closer. It's not, you shouldn't go like -4, then -3, and then -2. Because out here, right, at -4, it's way up there, and at -3, you're kind of down here, right? They want you to be getting like pretty microscopically close to this thing, and Desmos is a great tool to help you do that, right? So here I am 1/10 away from -2. So let's get 10 times closer, right? Let's get to -2.01 from that side, right, where I'm 10 times closer in on this thing. And it's showing me that, right, if I plug that into this, and you could do this by hand if you wanted to. I've done that in my classes before. Right? You could plug in -2.1 into this equation and see that it comes out to be exactly like -3.0099. And then let's get in even closer yet. We'll just do this one more time where we get 10 times closer. This is 1/100th away from -2. Let's go 1,000th. Okay, and I see that, right, I gain another 0 here and another 9, but it's getting closer and closer to -3 until exactly at -2, I am undefined. And let's do the same thing kind of on the other side. We'll start in really close. We'll do like -1.999, 1/1000th away from -2 on the other side, right? -1.99 and then -1.9. And you can kind of see, right, we're reading this table almost from bottom to middle and top to middle and trying to see what is this converging towards, right? These values from both sides seem to be getting closer and closer to that exact -3 that it sure looked like from my graph. Now we're confirming that from the table, right? That this was negative 2.89, 11 hundredths away from negative 3. Now we're only 1/100th away from negative 3. Now we're only 1,000th away from negative 3. Or sorry, yeah, negative 3. Right, it's definitely, all of my evidence seems to be indicating that we're getting closer to that negative 3 point. If I did that for g of x, right, do the exact same thing. I could do x2 and then g of x2 if I wanted to. Just make sure that this subscript matches that, right? If you add a table here. So for your g of x, we want to do the same thing, right? Start 1/10 away, then get a little bit closer, then get a little bit closer, negative 2.001. And you can see that this thing, in contrast with this was getting closer to negative 3. This is just exploding, right? This is getting closer and closer to negative 1.99, negative 1.9. Right? As I come from both sides, this one is going closer to negative infinity, right? It was negative 13, then 103, 1,003. If you added another 0 in here, you could probably predict it would be negative 10,003. And from this side, I'm at 7, 97, 997. Add another 9 here, it would be 9,997. One side is blowing up off to negative infinity, and the other side is blowing up off to positive infinity as you get closer to that value. So I've gone ahead and taken those two tables and put them back in our notes here along with the graph. And just to show once again, right, I have my f of x values approaching negative 3 as x gets closer to negative 2, and g of x that's blowing up off to positive and negative infinity. And so we're going to get into some specific language about this here that you will see over and over and over again in calculus if you take this. So this is pretty vital, important information here, just on some of the lingo around this. Both functions, f and g, have what is called a discontinuity. At that point where x equals negative 2. Right? Another way you can say this is that the functions themselves are not continuous. At x equals negative 2, at that specific point. Everywhere else, they are continuous, and continuous is like a fancy mathematical word for saying like it's smooth and connected, right? There's no bumps in the road, there's no breaks. Everywhere in this graph, right, it's connected. I could pick the smallest fraction apart, and I could go from like one point to the next. Every point on this curve is defined, except for there in both cases. Right? So in both cases, that negative 2 is undefined, and so we have what's called a discontinuity, a break in that function. Right? But the two types of discontinuities are very different from each other, as I can kind of see just from the graph. One is an asymptote blowing up off to negative infinity and positive infinity, and one is just this little hole. So they're very different in how they behave from each other. So we say function f, that's the one that kind of just looks like a parabola, the black one here. This is function f. Function f has what we call a removable discontinuity. At x equals negative 2. Right? This is kind of a double negative here, this removable discontinuity. I can make the not continuous piece not exist anymore by doing just one little thing, right? We could remove this discontinuity by plugging that hole. Discontinuity. By just defining, let's just say, hey, f of negative 2 does not exist. But if we made it be equal to negative 3, if we just said, hey, let f of negative 2 equal negative 3, well, we call that a piecewise function, right? Where I could say f of x is this equation up here, sorry, this one here, everywhere except for negative 2. And at negative 2, let's just define this to be 3. and that would fill that hole and remove the discontinuity. It would make it smooth again, because again, I can zoom in on that thing as much as I want to, and it is infinitesimally small, right? Like I can get in pretty much as close as I want with Desmos. If you get too close, it starts to do some funny things, but right, if I get even right to within a 10,000th away, that is just a little tiny hole that if I just patched it and said, hey, let's turn this not into a hole, but right, it paves the road over and makes it nice and smooth there. Right. So we say it has a removable discontinuity at that point. Function g, on the other hand, right, has a non-removable discontinuity. Right. There's nothing that I could do that would connect one thing to the next, right? I have this asymptote here, and that bridge is always going to be too far. There's no one value that I could plug that would fill it, right? So we have this is almost triple negative here, right? Like I am not able to make this not continuous part go away, right? It is there, it is stuck there, right? Which usually, right, those non-removable discontinuities show up as asymptotes. And these discontinuities, the non-removable versus removable discontinuities, really stems from what we see above here. It all hinges on this evaluation, this whether I'm getting a 0 divided by 0 or a 1 divided by 0. They're two different forms of a discontinuity, right? So if I come down here, you had f of negative 2. When I plugged that in, I got 0 divided by 0, which was undefined, right? And g of negative 2, I plugged that in, and I got 1 on the top and 0 on the bottom, which was also undefined, but they're very different forms of being undefined. This 0 divided by 0, this is called indeterminate form. Which means that nothing can really be determined, right, about the nature of the discontinuity. We don't know if it's an asymptote or a hole. It could be one of those holes that we saw in this example here. It also could be an asymptote. Right. There's really not enough information in just this to know one way or the other, right? A lot of people want to say 0 over 0 and automatically think that's a hole in the graph, like what we had above. It's often the case, but it's not always the case, and I might show an example a little later when it's not the case. But the 1 over 0, right? And really, it's just any a divided by 0, right? Where a is not equal to 0. Right? This is called infinite form. And this guarantees a non-removable asymptote in the graph. Right? So 0 divided by 0 might be a hole, might be an asymptote. Anything else divided by 0 is a guaranteed asymptote, guaranteed to blow up off to infinity or negative infinity or both. So we've done a little evaluation of these already, the 0 over 0 and 1 divided by 0, by looking at the the graph where we saw it should be approaching -3 for function f and infinity for g. We looked at the tables approaching -3 for function f to infinity and negative infinity for function g. But now we're going to try to show this algebraically, kind of the holy grail of mathematics, trying to get to this place where we can understand this and show it using just symbols. The graph and the table, they're great data points, but we want to be able to really prove that this thing is getting closer to -3. So that -3, there's a specific vocab term that's associated with that -3. So for function f, the number -3 is called the limit of the function as x approaches -2. Right? F of -2 is undefined, but the limit of the function as we get closer and closer to -2 has a value and is -3. And we write that with some symbols. We write LIM, the abbreviation for limit, of f of x. So then this little f of x, we usually just write it right next to it. And then underneath here, right, we say as x approaches -2 is equal to -3. Right? F of -2 is undefined, but the limit of the function f of x as x approaches -2 is equal to -3. Right? And we can find this, we can show it algebraically by doing what we did in the first lesson in chapter 15 here, by rewriting that function f of x in mixed number form. Right? So we're going to find that limit algebraically by rewriting f of x in that mixed number form from section 15.2. So we have our f of x was equal to x cubed plus 7x squared plus 13x plus 6, all divided by x plus 2. So what we want to do is actually do that division, divide this thing by x plus 2. And you can do that with the polynomial long division or the other little trick that I showed. I'm going to do it using the synthetic substitution. That's just kind of a quick way to do this. So again, synthetic substitution. That's too many. Right. We put in -2, the x value, right, that would make this denominator 0, goes up here. The coefficients of the numerator, the 1, the 7, 13, and the 6 go up there. Leave a little space. Right. We drop down the 1, multiply by -2. Right. Add these two things down, so 7 plus -2 is 5, times -2 again would make -10. Add those down, I get 3, multiply by the x value, the -2, I get -6, and then 0. Right. So that 0 is telling me, right, I have this remainder that's 0. So that means that x plus 2 is a factor of the numerator. It goes in cleanly. Right? So I could write this, right, that f of x, right, and these things here are the coefficients of the other piece, that quadratic remainder. So again, if this is the x cubed, I do one less than that, and I kind of like go 1 unit smaller in the exponent. So this would be an x squared, an x term, and my number term. So this is the coefficients of the quadratic remainder. And so I know that this f of x is really equal to that numerator I could factor out into x plus 2 times x squared plus 5x plus 3. Right? But the denominator would still be there, right? Divided by x plus 2 here, right? So this top, the cubic function, if I could divide by x plus 2, I could find that it would go in nice and evenly. Synthetic substitution or polynomial long division, either way, I'm going to get that, right? If I divided the numerator by x plus 2, I would get 1x squared plus 5x plus 3 as the other factor, and it goes in cleanly with this remainder of 0. So there's a couple of different ways I could write this, but one is to just say, let's do this as a mixed number, right? In mixed number form, I know that f of x is x squared plus 5x plus 3 plus this remainder of 0 divided by x plus 2. But this thing here, right, this 0 divided by x plus 2, this is equal to 0 always, right? It is equal to 0 everywhere on the graph except at x equals -2, where I'd do -2 plus 2 divided by 0, and I would get this undefined piece. But this thing doesn't really change the graph at all. So if I went back up here and looked at this, let's add in a function, right? F of x expression, right? If I type that in, f of x equals, I already have an f, I better do an h, of x equals x squared plus 5x plus 3 plus 0 divided by x plus 2, right? That thing, I was zoomed way in here, let's zoom back out to kind of show, right? This is the exact same as function f, right? They completely overlap each other, right? But that, right, I could take this away and you couldn't even tell that it was any different whatsoever, right? Because that plus 0 over x plus 2 has no effect on this graph anywhere except at -2, right? If I went here, turn this, right, I can still see, I'll get rid of the label here, right? Even there, right, it's undefined at -2. But what we do to get rid of the discontinuity is just say, well, let's just ignore this. What would this function be? What would this quadratic function be, right, at -2 if we just got rid of that, right? What it should be is -3. Right? So if I come back here, I can write, right, this function f of x is equal to x squared plus 5x plus 3 as long as x is not equal to -2. Right? And maybe you've seen it like this before back in Algebra 2, where you kind of you might have had those functions where you would have needed to factor out that numerator, and then you could just cancel this, right? And I can see that my f of x is equal to x squared plus 5x plus 3, but hopefully your teachers emphasize that I do need to account for this, right? I need to put in that as long as x is not equal to -2 part, right? These two things are synonymous. And so now, if I wanted to actually find this, I can evaluate the limit of this function as x approaches negative 2 by just seeing what would this be, right? If I plug in negative 2 for x into this piece, negative 2 squared plus 5 times negative 2 plus 3, right? I get that this would be 4 plus negative 10 plus 3 is negative 6 plus 3, which is the negative 3 that we were seeing the whole time, right? So the whole piece here, right, boils down to that synthetic substitution, get those quadratic pieces, and then say, like, that looks exactly like, right, these two things are completely identical to each other, right? They overlap each other in every way, but at negative 2, one is evaluable, right? When I get to negative 2 here, I can plug that in and actually get the negative 3, right? Whereas this one isn't. And so we just fill that hole, and we find what the hole is by simplifying this to just the quadratic, and then kind of just ignoring that it can't be equal to negative 2. We pave it over by defining f of negative 2 is negative 3. So very last piece, and then we're all done, I promise. You can do the exact same thing for function g of x, right? So we'll do that really quickly. For g of x, that was x cubed plus 7x squared plus 13x plus 7, all divided by x plus 2. And so if we do the synthetic substitution there, it's going to look the exact same, right, as what we did for function f. I'm going to use the negative 2, the value that would make the denominator be 0 here. My coefficients are 1, 7, 13, and then 7 now instead of 6. Right? And if I were to do this, right, drop down the 1, multiply by negative 2, add down, multiply by negative 2, add down, multiply by negative 2, and I see that I get this remainder, right? This remainder of 1 that says that this is not, right, that denominator does not go into the numerator cleanly. Right? So g of x in mixed number form would be 1x squared plus 5x plus 3 plus this 1 over x plus 2. Right? And if I tried to find the limit of this as I get closer and closer to negative 2, this I can't ignore. Right? Like as x is getting closer to negative 2, this is not 0 everywhere. This piece, right, is completely static, right? It does not change at all. It is equal to 0, right? This is always changing, and it changes drastically the closer and closer this thing gets to negative 2, right? This, the 0 divided by, if this is even like negative 1.9999999, right? You can have as many zeros in the decimal point as you want here. 0 divided by 0.00000000001 is still 0. 1 divided by 0.0000001 is 100,000 or a million or whatever. Like that changes a lot. So this, that limit then of function g of x as x approaches negative 2, right? That limit does not exist. Right? Think Lindsay Lohan yelling in Mean Girls, right, at her math competition. The limit does not exist. That is this case where it blows up off to positive infinity or negative infinity, and there's nothing I can do to remove it. The limit of this function does not exist. So big difference between the two. Get some practice in. This is really fundamentals of calculus, and next week we will dive right into actually finding the derivative, that instantaneous rate of change, using this 0 divided by 0. This indeterminate form is a very powerful tool of calculus. So